Good morning. In today's lecture, we'll study the basically our uh, good morning. In today's lecture, we'll study the hydrodynamic stabilities and the conditions at the interface. So, for the interfacial condition, we will derive the conditions in the planar geometry at the interface of two fluids. Then we can extend that concept up to the cylindrical geometry as well as for the spherical geometry. So first we should know the what is the stability. Now consider that object like this one, and here we are putting this an object. So if we displace this object, or we can say take this one, and we have an object here. If we displace it, we use some disturbance on it, we impose some disturbance on it, then it will displace either in this direction or in this direction, but after some time it will regain its original position. So this is basically a stable arrangement. This is a stable arrangement. Now at the same time, if we consider the object at this position, if we use some disturbance on it, either in this direction or in this direction, it will displaces, and it will never regain its original position after some time or after infinite time even. So this is basically an unstable configuration. Now take another picture or another arrangement like this one. Take some arrangement, one object here like this one. If we impose some disturbance on it in this direction, either in this direction, then it displaces, but you will see that the position is similar that its original one. So this is called neutrally stable, means there the stability doesn't depend on time. And one more we can say, it is if we have some object here, then if we use some disturbance or force on it, then if it goes here, it may be go to somewhere else, or if it is not going there, it will regain its original position. So this is basically conditionally stable. It is conditionally stable. So you can understand the difference between stability, instability, instability, you can say, then the neutrally stable and the conditionally stable. Now we use this concept in the flow fields, means the fluids when they are flowing. Even a fluid at rest may be unstable. So basically, in which condition we can say a fluid arrangement is unstable or not? See, we are considering here flow field, not a fluid. Fluid is just like an basically state of matter. So we are considering the flow arrangement, a channel or a basically cylinder, and we'll say whether the arrangement is stable or not. So a, a flow field is stable if we apply some perturbations on it, and after some time that perturbations die down, and that flow field regains its original position. Then we say that that particular flow arrangement is stable with respect to the applied disturbance. Remember, stability means the flow field should be stable for infinite number of perturbations, disturbance. Means the number of disturbance, the number of possible disturbance we apply, and system always regains its original position after some time, then we say that that arrangement is stable. If we apply some disturbance and system displaces and never regains its original position, then we say that the particular flow arrangement is unstable with respect to the given disturbance. That disturbance, basically that flow arrangement is unstable if it is unstable with respect to a single disturbance. But for stability, it must be stable for all the disturbances possible. Okay, flow in motion or at rest may become unstable corresponding to some distortion, and its flow characteristic may be different from the original one. If it is unstable, it disturbed, then definitely flow characteristic will be changed. But if it is stable, then after some time when it regains its original position, the flow characteristics will be same exactly in the basic state. See, we are considering the stability in terms of time. So this type of instability is known as temporal instability. If we are looking for the stability in terms of space coordinates x, y, z, or in cylindrical geometry r theta z, or in spherical geometry r theta phi, then this is called the spatial instability. Now, uh, that we have already discussed, if the system is slightly perturbed and the system and disturbance gradually die down, then the system is said to be stable with respect to these disturbances. But stability means it should be stable for each and every possible disturbance. And in case of instability, if it is unstable with respect to a single disturbance, definitely it is unstable. And the locus, which separates the two classes of states, defines the state of marginal stability. It is also called the neutral stability. Now, in case of uh, hydrodynamic stability, means stability in flow field, the first instability was thermal instability. Thermal instability. Actually, when we uh, heat a fluid layer from below, if it is T plus delta T and this is T, so if temperature is higher in the lower region, then there will be a convection and this fluid layer will be unstable. And this was called the thermal instability, and this was studied by Chandrasekhar in the early 90s, and after that some people are working on it. Here in this lecture, we will concentrate on the interfacial instabilities as per our topic. So in case of interfacial instability, we must have at least two fluids so that they can form an interface. More than two fluids are also be there, but we are considering here two fluid system. So just consider a two fluid system in basically planar geometry. We have two fluids and the interface is defined like this one. It is rho 2 and mu 2. The density of fluid is rho 2 and the viscosity is mu 2. The density of lower fluid is mu 1 and viscosity is mu 1. So if the fluids are at rest, and rho 2 is greater than rho 1, means that the arrangement is top heavy, then definitely this interface is unstable, and this type of instability is called Rayleigh-Taylor instability. Okay, in case of Rayleigh-Taylor instability, the fluids are at rest or they are moving with the same velocity means interface will not experience the relative velocity, so that, and the arrangement must be top heavy, so that the interface will be unstable, and this instability is known as Rayleigh-Taylor instability. Now, if the arrangement is not top heavy, then this is called statistically stable situation. If the fluids are at rest and the arrangement is bottom heavy, then it is always a stable situation. It is called statistically stable arrangement. If fluids are at rest and the arrangement is top heavy, it is called statistically unstable situation. If fluids are flowing with the different velocities, it is the velocity of the upper phase is u2, the velocity of the lower phase is u1, then this plane interface will also be unstable, and it will not be depend on the top heavy arrangement or the bottom heavy arrangement. Either rho 2 is greater than rho 1 or rho 1 is greater than rho 2, doesn't matter. If the interface is basically experiencing a relative velocity, definitely it will be unstable. And this type of instability is known as Kelvin-Helmholtz instability. Now, capillary instability is that when a liquid cylinder collapses in an infinite fluid due to the surface tension. If an infinite fluid collapses if a liquid cylinder collapses in an infinite fluid due to the action of surface tension, then the instability at the interface is called capillary instability. I think these are clear now. So the relative instability is the interfacial instability that occurs at the interface of two fluids having different densities. If high density fluids lie above the low density fluid, means the arrangement is top heavy. Remember, the fluid either fluids should be at rest or they are moving with the same velocity. The type of instability depends on the direction of acceleration of the accelerated fluids. Water suspended above oil, mushroom clouds of the atomic bombs. The hotter air from a strong blast gets pushed away by the cooler air in the atmosphere and the results in mushroom clouds. These are the examples of relative instability. You can just take some oil in a glass and put some water on it. You will see that after some time that oil will come above to the basically water, because water is heavy. So with the action of gravitational acceleration, and it will go to the lower region and oil will come to the above region. The physics in the relative instability is the basically action of gravitational force. Now, then Kelvin-Helmholtz instability, when two fluids having different physical parameters are placed one over other having relative horizontal velocity. Means it doesn't matter it is whether it is top heavy or bottom heavy, but the only case is that basically the interface must experience a relative velocity. Then the pressure perturbations will act and interface will be basically unstable. ठीक है, for this phenomena pressure perturbations responsible at the interface of the fluid layers. Here the pressure does work against the stability of the interface, and the interface gets destabilized. In sunrise or in sunset, the lower part of the cloud is cool and the less dense, so air at the top of the cloud moves faster than the air at the bottom and results in the Kelvin-Helmholtz instability. Uh, Third is capillary instability, that if a liquid cylinder collapses in an infinite fluid due to surface tension force, definitely that instability is known as capillary instability. The capillary instability of two fluid interfaces play an important role in film boiling, film voice condensation, and breaking of liquid jet. See, breaking of liquid jet contains Kelvin-Helmholtz and capillary both the instability. When we close a water tap, then the water breaks into drops. It is due to the surface tension. But when we open the water tap, then the velocity of the water is higher than the atmospheric air. Then at the interface, KH instability also occurs. Now, to study the instability, we have the oldest method, that is known as the normal mode technique. Now, in these days, people are using the uh, computational fluid dynamics to study the instability at the interface. But normal mode technique, which was used by Chandrasekhar for the thermal instability, and also for the also for interfacial instability, that was used by Shi and Lee in the early 90s. It is very beneficial technique which can give us the problem in terms of eigenvalues. See, if we have a disturbance, first we calculate or compute the uh, perturbation equations. We take the basic equations, then in the basic state we'll calculate the solution of governing equations. Then we use the perturbation theory, means we perturb the equations, and if we are doing the linear analysis, we calculate the linear equations in the perturbed state. After that, we use the normal mode technique. If we are doing the non-linear analysis, then we will calculate the different terms of different orders. Means first order, that is linear terms, then second order perturbation terms, then third order perturbation terms, and so on. So for the linear theory, if we have a perturbation like this AKRT, where R represents xi plus yj plus zk, with a typical amplitude describing in the kth disturbance mode, then what we will do, we will represent AKRT as AKR EPKT. See, this EPKT, we have taken the growth of perturbations exponential with respect to time, because we are dealing with the temporal instability analysis. This PK is the most important thing for us. This is a constant. We will take this one as a, this is as a basically complex constant, that pk can be written as pkr plus ipki, and our main concern will be the real part of this pk. So we use this AKRT. Each perturbation can be expressed like this, and then we will get the linear perturbed equations, which were partial differential equations. Now we will get those equations transformed into the in the ordinary differential equation, and where we will we can calculate the value of pk. Now, after solving those ordinary differential equations, we will get an expression in terms of pk. This pk is an eigenvalue, and so real part must be positive, sorry, negative, if it is, if you are looking for the stability. See, if pk can be written as pkr plus ipki. So if we are taking epkt, it can be written as epkrt into e to power I pkit. This is a complex quantity which can be written as cos pkt plus I sin pkt. So this is basically oscillatory instability, which is basically lies, the cos value lies between -1 to +1, sin lies between -1 to +1. But what about this value? Now see, if pkr is positive, then this value goes to infinity as t goes to infinity. Means at when time change, when we apply the disturbance, then with respect to time, the system will replaced from its original position, and there will be instability. So pkr is positive, means system will be unstable. Now if pkr is negative, then this perturbation tends to zero as t goes to infinity. Means after some time, system will regain its original position. So pkr is less than 0, means pkr is negative, then this is a stable condition. And now if pkr is 0, if pkr is 0, then we will have neutral stability. And if pkr is 0, we have some oscillatory instability there. Then it will depend whether pki is 0 or not. If pki is again 0, then the principle of exchange of stabilities are valid. And if pki is not 0, then definitely oscillatory instability is in the system. See, people can take e to power omega t, then we will have our total concern will on the omega r. If we are taking e to power minus I omega t, then our main concern will be omega I, because in this case minus I omega r plus I omega I will be minus I omega r plus omega. So if omega I is positive, system will be unstable. If omega I is negative, system will be stable. And the same thing is given here for the neutral stability, that omega I must be 0. And so this pkr is equal to 0 will be the case of neutral stability, or you can say it is the marginal stability case. Now, this is all about the interfacial instability. We have discussed the Rayleigh-Taylor, Kelvin-Helmholtz, and capillary. Then we have discussed the normal mode technique. Now, at the interface, if we are taking heat transfer and mass transfer phenomena, then the interfacial conditions we need to derive. So those conditions we are going to derive in the planar geometry. Remember, when we are taking heat transfer, definitely there will be a mass transfer because it is a coupled phenomena in case of interfacial instability. For example, just take water and water vapor, the interface of water and water vapor. If there will be heat transfer at the interface, then the basically water vaporize, and at the upper level that vapor will condense. So there will be a mass transfer from one phase to the other one also. So it is basically a coupled phenomena. So we are first taking the mass transfer condition at the interface. Later we will apply those conditions to solve the Rayleigh-Taylor and Kelvin-Helmholtz instability in planar geometry. So for the mass transfer condition, we have taken this interface, and remember this interface is changing with time because we are collecting the temporal instability of that interface. So we assume this one fx equal to 0 is the region occupied by the fluid above, means this region is fxt greater than 0, and this is fxt less than 0, and this interface is fxt equal to 0 because that is the interface basically. And this is given by fxt equal to 0. We consider a right small cylinder of height h, and the area A is situated at the interface, and its space coordinates are fixed, that is r theta z. Now we consider that part of right cylinder of height L is situated in the fluid above the interface and remaining part in the fluid below the interface. This L lies above, so this lower region will be basically your H minus L. And now we consider, as we are considering the mass transfer condition, we must have the conservation of mass, that is known as equation of continuity, and given by del rho by del t plus divergence of rho v. V represents the velocity and rho is the density of the fluid. Remember, this is the equation, generalized equation. So this mass transfer condition will be valid for the basically Newtonian fluid, non-Newtonian fluid, for incompressible and compressible fluids. Now we integrate this equation over the volume V. So if we integrate this one, rho dx cube, this is the volume element, and then use here the Gauss divergence theorem, this will be the area element. This is unit outward normal at the interface. So if we'll take the cylinder, then this is the volume of the cylinder, that surface area into length, and then the surface area into length, total value in two parts, above the interface plus lower the interface, and then the value of rho v at the interface. Now, as A is a constant because the surface area of the cylinder, and L was also constant, so we'll get this equation. See, L is changing with time. L is not constant basically, the constant is H, the height of the cylinder. L is changing with time because the interface is basically oscillating with respect to time. In that case, L is depending on time, so we'll take dl by dt and we'll get this equation. Now, as we know that the equation of the interface fxt equal to 0, and at the interface the normal vector can be calculated as the gradient of f. So, and unit normal can be calculated by gradient of f and dividing with the modulus of f, modulus of gradient of f. Using that concept, we can calculate the value of dl by dt. It is minus n cap dot dx by dt because it is a normal component. L is basically the normal component at the interface, and so we'll get this value. Now putting the value in the also df, the total value, the material derivative at the interface is df by dt to dt plus gradient f dx. So we'll get dl by dt is del f by del t upon mod of gradient f. And therefore the mass transfer condition becomes this one, rho u df by dt plus Vu. Vu is the velocity in the upper phase and VL is the velocity in the lower phase. Remember, we'll take the viscous potential flow theory, means velocity can be written as gradient of some potential function. Then this condition changes rho u df by dt plus gradient phi u dot that gradient f is equal to rho l df by dt plus gradient phi l into gradient. Now this is the amount of mass transfers from phase 1 to 2 or phase upper to lower, and this is the amount or rate of mass transfers from basically lower phase to upper phase. Here we are not taking any source or sink at the interface, therefore these two values are same. If we will use or will take some source or sink, definitely condition will be different. Now just think one that whether if there is no heat transfer or mass transfer at the interface, if there will be no mass transfer at the interface, then this rho u df by dt plus gradient vu into gradient f equal to 0. Density will never be 0, so this is df by dt plus vu dot grad f is equal to 0. Basically this is basically the normal velocity of the interface is 0, and that is called the basically kinematic condition, which says that if a fluid particle at the interface, it will remain at the interface throughout the analysis, means the normal velocity at the interface is 0. There will be no normal velocity at the interface, and that is called kinematic condition, but that is valid only in the case when there is no mass transfer as well as heat transfer, because we already stated that heat and mass transfer are the coupled phenomena. If there will be mass transfer, then definitely there will be heat transfer. If there will be no mass transfer, heat transfer will not be there in the case of interfacial instability. Now the mass transfer case is clear. Now we will look for the basically our heat transfer condition. For the heat transfer condition, we must have the fluids are thermally conducting. The fluids are thermally conducting, then we can use the diffusion equation, which is given by this one. dt is the thermal diffusivity of the fluid, and del 2t basically this is the Laplacian operator del square. V is the velocity of the fluid. Now we assume that the upper fluid had temperature Tu, the lower fluid has temperature Tl, and at the interface will be in the basically uh, in local thermal equilibrium, so the temperature will be same, so it is Ts. Means we are taking like this. This is the fluid we are taking. Here it is y, it is x. This is fluid which has height h2, and this is the fluid which has height h1. So this will be y is equal to minus h1. This is y is equal to h2. So in this case, the fluid has temperature T u. This is T is equal to TL, and in this case, this is T is equal to TS at the interface. This was in the basic state. So T is equal to TL, this one, T is equal to TU, and TL is equal to TU, which is TS at Y is equal to eta xt, because we are considering the local thermal equilibrium. Now, as we are taking the temperature and velocity depends on temperature, and then from the momentum equation velocity basically pressure depends on velocity, then definitely pressure will be a function of temperature, and then PV, where PV is the basically equilibrium vapor pressure. Then we use the Fourier's law, because we are considering the temperature change. Q is equal to minus kappa delta T, and then we will use the similar condition for the that cylinder that flow when that we have used earlier in the case of mass transfer. We'll take a cylinder at the interface and then we'll calculate the integration over the volume V. We will get this equation. Now see this equation. This comes through this from Fourier's law, that the rate of kinetic energy and latent heat will be equal to the difference between net heat flux. This is, if we take this part in the left hand side, it is basically K2 del TL by del Tn minus kappa 1 del Tu by del Tn. Okay, so this is called net heat flux. The total, the kinetic energy, the difference between the kinetic energy and latent heat released during the phase transformation will be equal to the net heat flux, where omega is the velocity component and omega n is the normal velocity of the interface. Remember here, this W, sorry, this W is the velocity of the interface, and this V1 is the velocity of the fluid phase 1, and this is the velocity of the fluid phase 2. And this V and N1 is the normal component velocity in fluid phase 1. This Wn is the normal component of velocity at the interface. And here L is basically this quantity which is known as the latent heat of the phase transformation. Now this is the equation which has been derived from the diffusion equation, and it is the most generalized equation. Now then, effect of temperature gradient is independent whether the system is stable or not. The system tends to be more stable or damped if the vapor is hotter than the liquid, because the protruding of the liquid to a hotter region will result in the evaporation and thus diminishing the protrusion. When vapor is hotter and there will be a heat transfer, then definitely the liquid will also evaporate. And if there will be a mass transfer there, then liquid comes into the vapor side, vapor comes into the liquid side. That vapor comes into the liquid side will condense, and that liquid comes into the vapor side will evaporate. And that evaporation and condensation basically phenomena will diminish the growth of perturbations, and system generally get stabilized in case of Rayleigh-Taylor instability. In case of Kelvin-Helmholtz instability, when velocity is there, relative velocity is there, definitely it has the inverse effect. Now, that formula we have derived, this formula is no doubt exact, but it is very tough to use in the terms of stability analysis, because the multiplication of these two terms and these two terms is becomes, we have a third order equation basically, which is very tough to tackle in terms of the analytical analysis. So what we do, we generally take the we generally take this equation in a simplified version suggested by she. This simplified version says we can neglect the effect of kinetic energy because it is very low in comparison to the latent heat at the interface. So in this formula we just neglect these two terms, and so we will get this minus L rho n, this Vn1 minus Wn is equal to the net heat flux, and that is the simplified version of this one. This S eta is basically the net heat flux, and this equation says the latent heat released during the phase transformation is equal to the net heat flux at the interface, and that net heat flux can be computed by kappa 2 del t upon del Tn minus kappa 1 del T1 upon del T1 upon del n. The normal change in the temperature with the kinematic, basically with the thermal conductivity, we can calculate the net heat flux. Now putting the value of Vn1, that is the velocity in the phase 1, that is Vu, and Wn, the value in terms of del F by dt and gradient F, we can get this equation. And this equation largely used in the case of instability analysis. Here that S eta is can be written as the kappa 2, and this is the temperature difference del 2 T upon del N, and this is minus kappa and del 2 T by del T1 up by del N. And so we will get the simplified version. And what we will do generally in the linear case, we expand S eta in the neighborhood of eta equal to 0. So we'll get S0 and at eta S dash 0 and so on. At equilibrium state, when there will be no heat transfer, then the that net heat flux must be 0, means the one kappa 1 del kappa 2 del 2 T by del N must be equal to kappa 1 del T1 by del N, so that this S dash S0 equal to 0, and we calculate S dash 0, and we will get this equation in the linear form as rho L rho U del F by del T plus VU gradient F alpha eta. Here, in case of potential flow, Vu can be written as gradient phi u. So L rho u del F by del T plus gradient phi u dot gradient F alpha eta. Remember, this equation is valid for all type of flows, whether it is rotational or irrotational. So we will use those equations in the next lecture to solve the Rayleigh Taylor and Kelvin Helmholtz instability. Thank you.